Class 5 of ME370. I'm going to continue on with, we introduced the 3D stress, 3D Mohr Circle in the last class. Let's do a little bit more with 3D Mohr Circle. I'm going to have some examples, so some longish examples. I'm also going to introduce thermal stresses, rotating stresses, and press fit stresses, but I'm not really going to emphasize those all that much. But I thought for completeness, thoroughness, it was a good idea to have them introduced, or at least just discussed in the class, because to have left them out seems to not be being a thorough professor. So recall that in three-dimensional stresses we had this 3D Mohr circle where we had sigma 1, sigma 2, and sigma 3, and always in that order and always descending, right? And sigma 1 could be 0, and sigma 2 is a slightly compressive, and sigma 3 is a more compressive principal stresses. Could be. But we always have that arrangement. And that one of the important consequences that we will come to find is that tau, the tau 1, 3, which is the comparison between principal stresses 1 and 3, turns out to be the largest possible shear stress that can exist in a cube. If you turn the orientation of the cube in the prescribed way, you would be able to find here is the orientation in which it's having the most amount of shear placed upon it. And therefore, if you're basing the criteria on whether it's going to be pass or fail on its shear strength, that would be the stress that you would want to calculate. And so we did it for simple arrangements, right? We did it for for some of the examples, we didn't even have any shear stress on the preliminary part of the problem, and it was just plain stress. And then we even did ones where we had already done them in like class 3, but we took those results and said, hey, for this plain stress condition, here's what the actual 3D Mohr circle is. But what would you do if you had stresses in all different kinds of directions, right? Well, we go back to what I described in class 3. Instead of doing Mohr's circle, we would find the principal stresses by finding the eigenvalues, right? So I just want to briefly go over that a little bit. Let's see. So once again, we could have the scenario here where we have like, and I'm not sure what this one's corresponding to, but I'm just going to draw them out. Remember, I mentioned this in maybe class 2 that we could possibly have shears going in on all faces, right? We could have some scenario where that might happen. So we have normal stresses everywhere. We have sigma x, and we'd have sigma y and sigma z, and then we would have, and I'm going to try to make them positive here. So in the positive x face right there, that would be my tau xy, and then here would be my tau yx right there, right? And then here I would have my tau xz, and then here would be my tau zx, but they would be equal to each other and opposite. And then here would be my tau, that would be the y face and the z direction, so it would be yz, and then this would be my tau zy, right? There are all of your stresses that are possible onto the thing. Well, there is some magical way that we could rotate this thing around and all those shear stresses go away, right? We could also, even weirder, find some other like really for 45 degrees kind of turn in all directions. Gotta get your head around that to be able to find the place where you have the maximum shear. But really what we need to do is just find what these principal stresses are, the 1, 2, and 3, and I don't know that those are 1, 2, and 3, but we find out what those 1, 2, and 3 are right here, and then we could just find the tau abs max by taking sigma 1 minus sigma 3 and divide by 2, right? And by way of the 3D Mohr circle, that proven to us that's going to be the maximum shear in this most complicated of scenarios. Well, I have it in I put it in Matlab. I think I just went ahead and made something more complicated here, where I took, I'm not even sure where I got this from, and I took 20, 15, and a negative 30. All right, so we have tension and compression, and then I gave some values right here. And if we go ahead and I made this into a matrix. It doesn't have to be arranged like this, but I kind of like it, you know. Right? And noticing that I went ahead and said that these off the diagonal are going to be equal to each other, right? And if you take a look up here, you can see that the diagonals right there. That diagonal is equal to each other. That diagonal equal to each other, and that diagonal equal to each other, right there. And here is the x, y, and the z. Right in there. But by just taking the simple eig command, I can get the eigenvectors and the eigenvalues. And it's the eigenvalues that I want. They don't, for whatever reason, I don't always get a consistent output from there. So, not that this is very educational to put this out there this way, but I'll do it anyway. Remember that we can, see, let me get rid of some of these things. We can get Matlab online, right? So I opened up a blank M file from this, and to encourage you to explore these note sheets on here. So we go into the note sheets for the class, and this is class 5, right in here. And here are our note sheets, and this will have the videos on them soon when I'm done with them. We go to class 5, and because you save these PDFs, because why wouldn't you? It doesn't take you much, but you know you want these nice things to catch along, and you could just highlight this, hit Control C, and then go over to your Matlab and hit Control V, right? And then you can save this. Maybe I'll save mine. Save as, let's see, 3D principal stress. Wow, .m. I guess I can't have numbers. Does it not let me? It says cannot start with the numbers. All right. It's a stupidly long name, isn't it? Okay, but that's fine. I don't care. And then I hit run. And if we open up D, right? That's the one we care about. I just double click on it. And there you go. Here's our 3 principal stresses right in there. So we can find what our we can find them. We could find what tau abs max would be. So maybe we want to write that as a code, right? And so we wrote tau abs max is equal to and so let me see in here, we want to have D, and that should be 3 comma 3 close minus D 1 comma 1 divide by 2 semicolon. Let me see what that comes out to. Evaluate. And did it do it? Yep. So we have an abs max of 32.19 is going to be our answer for this. And we don't need our update for right now. So anyway, you know, this is a useful tool that you might want to incorporate in some other fashion. And if you also are curious about what the eigenvectors represent, and I'm always looking at these, I say that we have in the, I think by way of the rows, is it rows or columns? I think it's the rows. Why am I saying this? Because I know that these are unit vectors, right? And each one represents one of the new axes, or a point from the origin, right? So it's a point in space from the origin, and going from the origin to that point in space is the orientation of the new axes. And they're all unit vectors, so I know that the sum of the square to the sum of the squares of this line has to be equal to 1. And I think so. I'm just seeing that 0.9, and I'm looking for the largest variable. I think this one might be, I can't remember if it's by rows or by columns, but those do give you the x, y, and z components of each of the vectors that represent that new coordinate axis. Now I have from another example that got done from class 4. I go through by hand and do the eigenvectors and eigenvalues and eigenvectors. I'm not sure that that's a good use of our time. So what I decided to do at some point, I think, instead of doing it by hand, I went ahead and I just gave it to you. There you go, right here. So I'm just going to narrate this. All right, so I did this by hand. And this is for an example that we did in the previous class here. We could, I think, class 4 bar Hoeken 3 principal stresses plus 16. No, let me try this right here for this. All right, so I'm going to have sigma x is going to be negative 13.1. And sigma y is going to be 18.4, and sigma z is going to be 0 because it's going to be plane stress. Sigma xy is going to be, and I don't care what direction it goes, it's going to be 27.9, and I'm going to make this one 0, and I'm going to make this one 0. Boom. All right, and save, run, and boom. And so here is the principal stresses we're saying is negative 29.39 and 34.7. 34.7. Let's see, is that what I got? I'll skip to the bottom. Let's see if we got that. Well, actually, we should have said that right here. 34.7, negative 29.3, and a 32. So let me take a look at this. And sure enough, abs max was 32. Okay, so I got the same result right in there. But let's look at how would you go about doing that. I mean, we did it in Matlab, but math-wise, right? So if you're in a graduate school class that's doing mechanics of materials, chances are that you'll run across having to get the eigenvalues, or any type of graduate school that you might go to. There's at some point you're going to have to do by hand to get some eigenvalues. So how do you do that? Well, let's see. What you're really doing is you're subtracting out lambdas from here, and you're trying to figure out what kind of lambdas will create when you take a determinant of it, make that equal to 0, right? So that these lambdas are going to be the special condition that makes this thing go to 0. And there's only there's only two lambdas that you can really find. So what you do is you take the determinant of this, and so you multiply this times this minus that times that, right? And what you're going to do is you're going to get a quadratic, right, of lambdas. And from that quadratic right there, you get a b plus or minus the square root of b squared minus 4ac divided by 2a, and you stick in the coefficients that you have there, and you end up with 34.69 and negative 29.39, and that's what we got right there, right? And if you get one of the eigenvectors, so I didn't do this like for a long time. I think I learned this in undergrad at some point, of how to get the lambdas out, and they might actually make a little bit more sense when you see these lambdas, when you can see this done in the context of a little bit more linear algebra, worked out symbolically. You'll see what when that situation arises. I should have written that out that way. But like if you want to find out the eigenvectors, what you do is you go back up to this top thing and you plug in one of the lambdas for one of these, right? And then you put in what are these coordinates right here. This Rx and this Ry. And what you end up finding here is when you go through this, and you know that the top row right here is that times I and that times j, right? And so if you take the square root, if you divide that by the square root of its of the sum of the squares of it, that's the magnitude, you get a unit vector. And that unit vector right there is going to be what gets represented by this. That's going to be the axis that corresponds, the vector that corresponds with that principal stress, right? So you're going to have like, let's see, what did I get here, right? I got for the vectors, right? You see, I got the 8636 and 5042, and you get the 8636 and the 5042 right here. So I guess the answer is it's the columns, right, that are going to mix up right in there. And the same thing here you're going to have for the other eigenvector is going to be that right there. So there's the eigenvectors and the eigenvalues and the eigenvectors to be done in the case of three-dimensional stress, where you have more complicated situation. So I'm going to move on to probably some examples. This already went on for 17 minutes. I don't think this video is really all that much helpful in this first part of the lesson, but I did want to include it because it does tie in to some of the other aspects of looking at the three-dimensional version of stress. So thank you.